Hi everyone, thank you for joining AWM Pitt Grad Seminar. Today we have two speakers. Our first speaker is Paula Truöl, and she is a Postdoctoral Fellow from Max Planck Institute for Mathematics. And our second speaker is Agnes Mantoni. She's a PhD student from University of Münster, Germany. So our first speaker, Paula Truöl, will talk about knot, concordance, and notions of braid positivity. And our second speaker will talk about introduction to G2 holonomy. Please, Paula, you can go ahead.
Thank you. Thanks for the introduction and thanks everyone for coming. So, I am going to talk about knot concordance and notions of braid positivity, which was roughly the title of my doctoral thesis. I defended my thesis in June this year in Zurich, in Switzerland. But I wasn't sure about the audience of this talk, so I will try to be very general in the beginning and give a bit of an introduction into knot theory and then show you a bit what knot concordance is, and in the end try to tell you a bit about the type of questions I'm thinking about in my research. So let me start talking a bit about knots. I brought two pictures for you of knots. You can see on the left-hand side the knots that appear in sailing. Knots also appear in various sciences. They appear in statistical mechanics and quantum computing, but also in biology, as we can see here on the right-hand side. That's like a picture of knotted DNA from a biology paper from 1985. But so today here we want to focus on the mathematical perspective of knots. So let me define for you what is a knot. But let me first say that you really see knots very often in your everyday life. So when you tie your shoelaces, it's actually a knot. But I want you to think of your shoelaces as with the ends glued together. So as the Encyclopedia of Knot Theory puts it, you can really think of as a knot as when you start with a piece of string, you tie a knot in it, as I did here in the second picture, and then you glue the two ends of the string together. So we get a something like in this third picture. And of course, this is a bit informal, so let me give a bit more formal definition. A knot is a simple closed curve in three-dimensional space. Now, in knot theory, we usually like to think of the free sphere as the surrounding three-dimensional space for our knots. But if you're not so familiar with that, you can also think of Euclidean free space, as it is just the free sphere is just the one-point compactification of Euclidean free space. You only have to add 1 point at infinity. And so to be even more formal, what I mean here with a simple closed curve is I mean a smooth submanifold of the free sphere, which I want to be diffeomorphic to the circle S1. So the circle S1 is really the unit circle in the two-dimensional plane. And now I consider objects like this unit circle, but embedded in three-dimensional space. So they can look more complicated than this trivial knot that I can draw in the plane. For example, as in this picture I have with the strings. So let me give you some more examples. The first picture here is really the knot I tied into the string above. Then we have the trivial knot, which we also call the unknot. And we have 4 more knots, and these knots are drawn in what we call diagrams. So basically, we draw two-dimensional pictures of the knots that live in three-dimensional space, and we draw them with these what we call crossings, where you can see that one strand of the string passes over the other strand. We draw them with a small gap here, so that you can really see where this passing above happens. And so this knot here and this knot here have one crossing each. Then we have a knot with 3 crossings and a knot with 4 crossings. And I could draw many more knots for you. In fact, I can draw infinitely many knots. But let me not do this, but instead try to give you a bit of a big picture of the area of math that I'm thinking about, which is low-dimensional topology or knot theory. So as a bit of motivation to tell you what we do in low-dimensional topology, well, in topology, we study properties of spaces that are preserved under continuous deformations. And this means the following. So if you consider the 3 objects that I've drawn here on the top, so a cube and a snooker ball and a donut, for me, mathematically, they would maybe be a cube and a ball and a solid torus. Then continuous deformation allows me to transform this cube into the ball by gradually pushing in the corners of the cube. But I cannot transform by continuous deformations the ball into a solid torus. I would really have to cut it in pieces and re-glue them. But continuous deformations only allow us to bend and stretch and move around objects in space. And then in low-dimensional topology, we focus on spaces, manifolds of dimensions 4 and below, such as this cube and the ball and the solid torus, but also one-dimensional objects like knots or two-dimensional manifolds like surfaces, for example, the surface of a donut or the Möbius strip, or this surface here on the right-hand side, which consists of basically 2 disks, the blue and the green disk, and they are connected by 3 half-twisted bands. And then, in fact, the boundary of the surface here on the right-hand side is a knot again. So these are the types of objects that we're studying, and we study them up to continuous deformations. So what does this mean in our case of knots? So 2 knots, K and J, are called isotopic if there is a continuous deformation of one of the knots into the other. And to be more precise, if there is an orientation preserving diffeomorphism, a smooth map from S3 to S3 that maps one knot to the other. This gives us an equivalence relation on the set of knots, and we usually study knots up to this equivalence relation. So if 2 knots are isotopic, for me, as a knot theorist, they are actually the same. And so in the examples that I've given you, I've actually only shown you 3 different types of knots, 3 different isotopic classes of knots so far. Since this picture of the unknot here can be, for example, transformed into this second picture that I've shown you, but with 1 crossing. I guess it's not too hard for you to imagine that you can really find an isotopy of the second curve here. So you move around this thing in free space. I have a piece of string here, but I'm not sure you're gonna see too much on your screen. So if you have this 1 crossing of the knot, we glued the 2 ends together. It's not so hard to see that this piece of string can be transformed into this round trivial curve. And similarly, this third picture here is also just yet another diagram of the unknot. Then here, the knot I tied into the piece of string is just drawn here again in a more formal diagram and try as an exercise maybe to see that the second diagram is actually a picture of the same knot as this third diagram. There's an isotopy between the two knots. And then, yeah, there's also the figure 8 knot. And again, there's many more knots, but let me not tell you too much about this. But instead, let me give you some reason why we would study knots in general. And there's two results that I want to tell you about that tell us a bit why should we study knots in general. And the motto here is that knots help to understand 3- and 4-dimensional manifolds. So I want to give you 2 examples, and if the precise statements here don't make too much sense, don't worry. It's more like a motivation. The first motivation is that knots provide blueprints for constructing 3-dimensional manifolds in the following sense. So there's an important theorem in the area, which is by Licorice and Wallace from the 1960s. And the theorem is that basically any 3-dimensional manifolds with certain adjectives attributed to it can be obtained from the standard 3-dimensional sphere by performing something called de-insertory on a collection of knots. So this means that we start with the 3-dimensional sphere and we cut out thickened up knots from that sphere. So more formally, we cut out tubular neighborhoods of these knots, which are solid tori that can be knotted from the free sphere, and we glue back in other solid tori along their boundaries. And in this way, you can, in fact, get any oriented, close, connected free manifold. So knots can really help us to understand and visualize 3-dimensional manifolds. The second thing I would like to tell you about is that knots can be used to reveal exotic structures of 4-dimensional manifolds. There's a result from the 60s to 80s by many authors that I've listed here for you, which tells us that Euclidean 4 space stands out among all Euclidean n spaces in that it has uncountably infinitely many smooth structures, other than all the other Euclidean n spaces, which all have a unique smooth structure. And this can be shown using something called topologically but not smoothly sliced knots. And this goes a bit more in the direction of research that what I'm studying. So in the following, I would like to introduce sliced knots to you and explain you a bit what they are and what you can do with them. Okay. So right. So let's talk a bit about sliced knots and knot concordance. And the motto here is that a sliced knot is the next best thing in a way to the unknot, which was this trivial unknotted circle in 4 dimensions. So what is the definition? The definition is that a knot K in S3 is slice if it bounds a smoothly embedded disk D in before the 4-ball bounded by S3. Okay, so what you should imagine is you have, that you have a ball, a 4-dimensional ball, which I cannot really draw for you because 4 dimensions are hard to draw. But this is like a dimension reduced picture. It looks a bit more like an egg maybe, but okay, that's the ball. And as its boundary, you have the free sphere S3. And now you should think of the knot K in the boundary. Here I draw just 2 points. And then we want a disk inside the four ball with boundary this given knot. Okay, so I've written it also here. We want a subspace of B4 that is diffeomorphic to a disk, two-dimensional disk, such that its boundary is the given knot in S3, which we think of as the boundary of the four-dimensional space. Now, what is an example of a slice knot? The unknot, so this trivial curve, is an example of a slice knot because it actually even bounds a disk already in three-dimensional space. You can draw the circle in the plane and you can fill it up with a disk. And this is really a disk like the disk we want to have here. And you can think of this disk also as living in four-dimensional space. It's still there, so the unknot is sliced with this definition. Now, a schematic of the more general situation would be here on the right-hand side. I've drawn, or I tried to draw a picture of four dimensions where we have one dimension here and two dimensions sort of in this direction. And then we have the knot living in this three-dimensional space, and we have like a schematic of a disk in the four-dimensional ball bounded by this knot. Okay, so in which sense is a slice not the next best thing to an unknot? Well, as I said, the unknot bounds a disk in S3, and there's a proposition which tells us that a knot is actually isotopic to the unknot if and only if it bounds a disk in three-dimensional space. Not every knot is sliced. This was shown by Fox and Milner in the 60s, but it can be a very hard question to determine whether or not a slice. And so, in fact, if we look at this blue knot that I've drawn here on the right-hand side, which is called the Conway knot, it was an open question for more than 50 years whether this knot is slice, until it was shown by Lisa Piccirillo in 2020 that this Conway knot is not slice. And this is an annals paper, so it's like not a super easy result. It can be a really hard question to determine whether or not to slice. Okay, now I told you about isotopy, which is an equivalence relation. Now I would like to tell you about another equivalence relation that is more related to this four-dimensional notion of sliceness. So concordance is an equivalence relation that generalizes isotopy between knots to dimension 4. The definition is that two knots K and J in S3 are concordant if they co-bound a smoothly embedded cylinder in the four-manifold S3 times 0, 1. And written a bit more formally, there's a submanifold C of S3 times 0, 1, which is diffeomorphic to a cylinder S1 times 0, 1, such that the boundary of C is K times 0 union J times 1. And I've drawn a schematic for you here. So this big cylinder should depict S3 times 0, 1. On the left-hand side, in this copy of S3, we have a knot K. And on the right-hand side, we have a knot J. And then in the middle, this thing which looks a bit like an elephant trunk, maybe, this is supposed to depict the cylinder C that co-bounds our given knots K and J. Okay. So now, as I said already before, this is an equivalence relation. And in fact, if we look at knots up to concordance, if we look at concordance classes of knots, together with a certain operation called connected sum that I won't really tell you about, this forms a group, a countable abelian group that was defined and studied by Fox and Milner in the 60s. Now, in this group, what is the relation to sliceness? In this group, the slice knots, so the ones that bound disks in the 4-dimensional ball, these are the ones that represent the identity in the element in the group, because these are the knots that are concordant to the unknot. They are equivalent under this equivalence relation to the trivial knot. Okay, but yeah, to get closer to this type of questions I'm thinking about, let us consider the following proposition. So if you look at the definitions of isotopy and concordance that I gave you, if you look at them close enough, you can observe that if you have two knots K and J and they are isotopic, then they are also concordant. The other way around, however, is in general not true. So if you have two knots K and J and they are concordant, then it's usually not true that they are isotopic. And the example, or an example, is any non-trivial slice knot. So any knot that is concordant to the unknot, but not isotopic to the unknot, gives you an example of that. Now, in my research, I tried to answer questions like the following. So basically, I'm interested in looking at this direction, which is not true in general, that concordance implies isotopy. I'm trying to find or study classes of knots for which the converse holds. So the question is, for which classes of knots do we have that concordance implies isotopy? Okay, let me mention one type of knots where this is true. So it was shown by Litherland in 1979 that it is true that concordance implies isotopy for so-called algebraic knots. And I'm not really going to define algebraic knots for you, but give an example. So all the T, P, Q torus knots, where P and Q are positive integers, which are co-prime. These give an example of algebraic knots. They are defined as the knots that you can draw on the surface of a solid torus, like here on the right-hand side. So they wind around P times in one direction of the torus and Q times in the other direction. But you can also see, or they also arise in algebraic geometry as zero sets of certain polynomials. So if you look at the polynomial in two complex variables, x to the p minus y to the q, and you take the zero set, v of f should be the zero set of the polynomial, you look at this in the complex two-dimensional plane and you intersect with a sphere around the origin, you get a one-dimensional manifold, and this is actually this torus knot that I can also draw on the torus. Anyway, so these torus knots are algebraic knots, and this definition of algebraic knots is very related to this construction of coming from complex algebraic curves. Okay, so Litherland showed that concordance implies isotopy for this class of knots, and much later, a couple of years ago, Baker conjectured that concordance implies isotopy for a class of knots called strongly quasi-positive fibered knots. Fibered knots are knots that where their complement in S3 admits like a certain nice structure, a locally trivial fiber bundle over the circle. And strongly quasi-positive knots, I want to give you an example in a minute. I won't give you like the precise definition, but try to explain a bit what they are. And so, yeah, I won't go much into the details of why Baker conjectured this, but he conjectured that for this class of knots, concordance implies isotopy. Now, one of the main results of my PhD thesis is the following theorem, which I showed last year, which tells us that if we look at this conjecture by Baker and we remove the assumption of fiberedness, then the conjecture is not true in a certain strong sense. Namely, the following is true: every non-trivial strongly quasi-positive knot, where non-trivial means not the unknot, is concordant to infinitely many pairwise non-isotopic strongly quasi-positive knots. So this means I start with a strongly quasi-positive knot that is not the unknot. I look at its concordance class, and I can construct for you infinitely many strongly quasi-positive knots in the same concordance class that are not isotopic to each other. So it's very much not true that concordance implies isotopy for these strongly quasi-positive knots. All right, so as I said, I will try to explain a bit what strongly quasi-positive knots are. I've drawn some pictures to try to explain this. So basically, every knot can be drawn as something called the closure of a braid. I've drawn an example of a braid for you. So I've drawn a braid on 3 strands here in picture A on the left-hand side. So you see these 3 strings, and they are allowed to cross each other in 2 ways, like either the first strand goes over the second strand, or the second strand goes over the first strand, and similarly between all the other strands. And then the closure operation means that we glue the 3 ends on the top of this braid to the 3 ends on the bottom, and you get something like the picture in the here in the middle, which often is a knot, can also be a link, which is something of several components. And now this for these strongly quasi-positive knots, they come associated with a certain surface in a particular form that I've also drawn for you here on the right-hand side. So, and you should try to see that this braid here in the middle, or the braid closure in the middle, and the surface on the right-hand side are really related. So basically in the surface, I have 3 discs like so, which are which come from the 3 strands that I had in the braid. And they are connected by half-twisted bands, where the half-twisted bands correspond to the crossings. So this, sorry, this blue band here corresponds to the crossing I have here between the first and the second strand. And similarly, this band corresponds to the second crossing. This long band corresponds to these 3 crossings stuck together, and so on. And yeah, a knot is called strongly quasi-positive if it bounds such a strongly quasi-positive, how we call it, Seifert surface, which is the surface of this certain form with disks that are connected by positive half-twisted bands. So really, I have all these bands like this. And you should try to see that this band really is the same. The boundary of this band is really the same as the crossing we see in the middle picture. Like you just move this small crossing here a bit over to get this picture. I'm sorry. So yeah, I hope this makes a bit of a sense. This is the definition of strongly quasi-positive knots, vaguely. So they arise with certain as boundaries of certain nice Seifert surfaces. And now, just to finish off, I will be done very soon. I just wanted to give you like really one basic main idea of the proof of my theorem, which again is that if you have a non-trivial strongly quasi-positive knot, is concordant to infinitely many such knots. All right. So this is really a proof by picture or proof idea by picture. We have seen, or I tried to explain to you that these Seifert surfaces come in a certain way with these disks connected by half-twisted bands. And then the idea of the proof is really a certain construction where we take another quasi-positive, strongly quasi-positive surface in a certain way, which is like basically an annulus with a knot C tied into it. And then you look at two bands of these two surfaces and you cut them open and connect them in a different way. It turns out that this construction is such that the resulting knot is a knot which is concordant but not isotopic to the original knot. And it turns out that it's strongly quasi-positive again. And this is basically the main idea. We can iterate the construction to find infinitely many such knots. And yeah, this is how we can prove the theorem. So let me finish here, and thank you very much for your attention.
Thank you so much for the talk.